Hi! Today we're going to learn about sampling distributions basics. So, before we get started, we have to first understand what a sampling distribution is. So the first thing is, I know you guys might be thinking, what you guys might be thinking is, wait, we already know this. We already know what a sample distribution is. That's just basically a distribution of our various samples, and they can be random samples or not random samples, I guess. But sampling distributions is something different. So in a sample distribution, you have, let's say you have a histogram. So you would have your little bars and your values, and you would have, let's say, 5 to 10 to 15 to 20 to 25 to 30. And then you would have these values, and these would be the individual values that you got. So the number of individual values, so let's say this would be 2, the value of this would be 2, the value of this would be 1, 2, 3, 4, then 3, then let's say this is 2, let's just say, even though it's not, and let's say this is, let's just move this around. Let's say these are both 2. Okay, so this is what a regular sample distribution would look like. And a sampling distribution is similar to this, but it's not exactly the same. So in a sample distribution, we have our samples and their corresponding values, and we just put them into the histogram. What a sampling distribution is that it shows the values of the averages of these samples. So you have a sample, and you have the sample size. Okay, so let's start into this. So you have the population, which is a total. So let's start off with the basics. So you have your population, which is the entire selection of individuals, population, and then you have your sample, which is basically the group that you're sampling, or you're getting your data from. So you have your sample, and so in the sample distribution, you just have the values that you get from these samples. So let's say, yes, so you just have the values that you get from your samples. Now in a sampling distribution, you have the averages of those values in your histograms. So let's take a look at an example. So let's say that you had a spinner, and this spinner was divided into 4 sections, each with a different value, 1, 2, 3, and 4. Okay? And or let's say each has a different letter, A, B, C, or D. A, B, C, or D. And then you have your histogram off to the right. You have, or this would be a bar graph, but A, B, C, and D. Okay, and then you have values. 1, 2, 3, 4. So in a sample distribution, what you would do is you would spin the spinner and then record whatever value came out, and then just put that in the histogram. So you would, let's say, have 2 A's, 3 B's, 1 C, and 4 D's. So this would be what your sample distribution would look like. Now let's get into what a sampling distribution would look like. So in a sampling distribution, you would have the same setup of a histogram. It would basically be the same setup. So, oops, that was wrong. A, B, C, and D, and then values 1, 2, 3, and 4. 1, 2, 3, and 4. But what the thing is you would have your sample size, so the number of samples you take. So let's say your sample size, which is n, it's always n, is 4. And so in one sample you would get, in sample 1, let's say S1, you would get A. Oh yes, the other thing is, when you have a sampling distribution, you have to have numbers as your values. So let's say instead of A, B, C, or D, it's 1, 2, 3, or 4. 1, 2, 3, or 4. Okay, so let's say that you get, in your sample size of 4, let's say this is the sample size, yes, of 4. Let's say you get 1, 3, 5, not 5, you can't get 5. 1, 3, 3, and 2. And then you take another sample, and then you get as 2 is equal to 4, 4, 4, and 1. Okay. Also, the other thing I forgot to mention is that these values have to be in a histogram shape. So it has to be 1 to 2, 2 to 3, or 1 to 1.999, 2 to 2.999, and 3 to 3.999, and 4 to onwards. So 4 to 5. Okay, so it has to be in a histogram format. So now we have our samples, and in our samples we have 4 values. So in a sampling distribution, we show the values, or the averages of these values. So the average of this value would be 3 plus 3 is 6, plus 2 would be 8, plus 1 would be 9/4. This would be 4 plus 4 is 8, plus 4 is 12, plus 1 is 13/4. And so this would be, so this 13/4 would be would basically fall in this category over here, so we can have 1. 9/4 would fall into this category over here, so we have 1. So basically we're just putting down the averages of these values, the averages of our samples. That's what goes on a sampling distribution. Okay, so now that we know what a sampling distribution is, let's talk about some of the basic rules. So the first thing to note, or some of the basic things that we should note about sampling distributions. The first thing to note is that it's not the same as a sample distribution. So in a sample distribution, we just show the values on a histogram, or on whatever it is. In a sampling distribution, we show the averages of these values. So we show all the possible averages of these values. The second thing is that as n increases, the range decreases. Okay, so let's think about this for a second. First, we have to remember what n is. N is equal to the sample size. Okay, so as we increase the sample size, the range of our histogram is going to decrease. So what does that mean? Well, it means that our averages are going to get closer and closer and closer together. Now let's think about why. So why would this happen? So if we increase the sample size, what does that mean we're doing? Well, we know that we're taking the averages of our samples. So if we increase the sample size, we're going to increase the value that we're dividing by, which is n, the value that we're dividing by. So if we're increasing the value that we're dividing by, according to the law of large numbers, our probability, or our, not theoretical, our experimental probability, or what we get from doing these random samples, would get closer and closer to the theoretical probability. But that doesn't really help us with what we're looking at here on a histogram. What it really matters is whenever when we're taking samples, we're going to get outliers, or values that are not close to the actual average. So let's say you have a cluster of values here, and then you have this outlier, and this is on a number line. So the more values you have, and if you're taking an average, the more values you have, the less impact this outlier will have on the average. So if you have 1, 2, 3, 4, and 5 values, 6 values, this is going to have, let's say, a big impact on the average. Let's just say a big impact. If you have the same thing, but then you have a lot more values here, let's say, I don't know how much this is going to end up being. Let's say in this general area you have 100, so it goes from 6 before to, let's say, 100 values, then the impact that this one outlier is going to have is going to be a lot less. So that means that as n, or the sample size, increases, the impacts of the outliers are going to decrease. So that means that the range of these averages is also going to decrease as these averages get closer and closer together. The third thing is that in a sample distribution, n remains the same. So what does this mean? Well, it means that in our distribution, in one distribution, there's only going to be one n value. So for every point or every value on this distribution, there's going to be one sample size. So how does this help? Well, we remember earlier, or from here, that as the sample size increases, the range decreases. So if we're constantly changing sample sizes, then we're not getting a good distribution of values, or we're not getting a good representation of the actual population. So if we have to keep the n values the same, or the sample size is the same for each data point on there, or data value on there, in order for our histogram to actually be, or our plot to be representative of what it's trying to describe, which is the population. And then the last fourth thing, which says that the true average is the average of the population. So basically this is just saying that the actual average on our histogram is going to be the average of the population. So we can do this is just by having n equal the population size. So the sample size, if it's equal to the population size, then we'll get the same, we'll just get the same averages for everything. So we would just have, it would just look like this. So if n is equal to population size, you would just get this bar of one value. And let's see how this plays in with our other rules too. So this would not be the same as a sample distribution because it wouldn't show this one value. Or it would, but it wouldn't, yes. It wouldn't really follow this one because this one doesn't apply to this. In our second rule, it says as n increases, the range decreases. So the range is just 1 point now. So it follows that. The third one, in a sample distribution, n remains the same. So n would just remain the same as the population size. And for the true average is the average of the population. So the true average can be seen because it's the only average possible. So the only average possible when n equals the population size is the average of the population. So that plays in with our fourth rule. Today we learned about sampling distributions. Thank you for watching this video.